Okay, in continuation of our optimization with respect to the neural net weights and updation and so on, we are going to be looking at how we can also reduce the computation from the softmax layer. And then I have just added one more layer for the sake of understanding, which is the softmax layer. On obtaining the values in the output layer, we are applying the softmax here, right. The softmax is a normalized exponential function as given in this equation. All right. So, the normalization comes from the summation of all the word value that we have computed. Okay. So, each one will have the probability value here, and the summation of all of these would lead to 1. This we know very well, right. And this is a flat hierarchy. That means, we compute the probability for every word in the vocabulary once the output layer computation is completed. All right. So, the depth of this layer is 1. Okay. So, keep this in mind, and then here is where the error correction starts. So, from here we actually update the context vectors based on how much the value moved from the actual target, and then update the h values and then the embedding vector values, and we keep doing it until we finally get an equilibrium where there is no more change that you can find. Okay. And then if you look at the softmax layer at the bottom, so every time when you do the or when you compute the probability for each word, you will see this, right. For every word this is being computed. So, assuming now that if you are going to be having a million words in your vocabulary, so we have to be doing this operations every time, right. For every word the probability has to be obtained using this equation, right. That means, we are going to be doing it 1,000,000 times. So, we do the summation once, and then taking the exponential for each and every output layer that we get will be done, and that increases the computational complexity. Okay. So, this is again a very good place for you to optimize our computation. All right. So, we try to reduce the computational complexities by taking subsampling, removing some of the samples that are not really contributing to the understanding of the word, and then we applied negative sampling, wherein we add 5 words that don't come as part of the context in the case of skipgram, and then necessarily make them as 0, so that the computation of the context vectors were done only for the positive context value on the negative samples. That means, we are doing only for 0.1% to 0.05% or even lower, depending on what is the number of negative samples that we are looking at. So, the third one that we are looking at is improving the computational capabilities with respect to doing something with the softmax layer. So, we are going to be looking at what we are going to be doing in the softmax layers in the next from the next slide onwards. So, before getting into how we can reduce it, let us keep those words in the vocabulary in a binary tree format. Okay. So, we are going to be looking at only the balanced binary tree. I am sure you know what binary tree is and a balanced binary tree is. A balanced binary tree is one where you will have a binary branch for every node, and for example, for the node 4 we have 2 leaves, okay, node 5 and so on. So, if you start with the root node, you have 2 nodes, and then for the second node we have 4 and 5, for the third node 6 and 7. So, that means the binary tree is balanced. I am sure most of you know about it. This is just to refresh your memory. Okay. So, we place the words in the leaves. Okay. That means, all the words would be available in this form, okay. And we know that how to reach each word from the root node. Okay. So, this is your root node, and if you want to reach W3, I have marked that in red. So, you take a left, reach the node 2, take a right, reach the node 5, and then you get W3. So, the path is unique for each and every word. So, this is one way of constructing the binary tree. So, how do we get these in this order? So, there could be multiple ways of doing it. One is we can take the vocabulary and then place them at random. So, there is no relationship between W and W2, it is just placed at random. So, another way is to look at the word net where the words are arranged in the easer relationship. I am sure you remember the easer relationship I spoke about in some of the sessions earlier. So, for example, if you look at the color as one example, we can say red is a color, blue is a color, and so on. So, these types of easer relationship is captured and the words are arranged accordingly. So, when you use a easer relationship, the binary tree is unbalanced, it is not going to be a balanced binary tree as I have shown in the example here. And then we can use the frequencies of the words in the corpus. So, for the most frequently occurring word, we can use a shorter path, and then the least occurring words we can probably have a longer path in the binary tree. Again, if you go with this approach, the tree is not going to be balanced, it is an unbalanced tree. So, there are ways of arranging the tree. Let us assume that we have arranged it in some form and it is available for us for the computation for the sake of this lecture. As I mentioned earlier, the path is very well known for any word. And then at every step, right, from you start from the root nodes, you want to make a left or a right. So, you make a binary decision at every node in order to reach the word, and then the length or the number of nodes that you have to cross is given by the relationship. So, this will give you the length for a balanced tree. So, as I mentioned earlier, the words can be arranged in any one of these ways. All right. So, now let us take an example with 8 words. We want to find out the probability for each word, which is normalized as we had seen in the softmax. So, the goal is to really find out whether we are able to get to the level of softmax without having that complexity of softmax. All right. The path is given here at the bottom. I am just going to make up some values initially, and then see how this could be translated into the word to vec model. All right. Let us first start with the root node 1, and then I am trying to find out the probability of the word W3. So, how do we find out? Let us start with this first. So, when I start from node 1, so I need to go to node 2, I traverse to the left, and then I traverse to the right from 2 to 5, and then to the left to reach the value. So, let us first assume that the probability as 0.53, and then the rule for filling in the probability when you move from 1 to 3. So, it has to be balanced and the sum of the probability should be equal to 1. So, the value is going to be 0.47 here. So, that means the P n left plus should be equal to 1. So, this is the rule that we have to apply. Let us assume that we are able to find the probability of reaching from node 2 to 5 as 0.79, then probability of reaching from 2 to 4 would be 0.21. All right. So, if you start doing all of this to the left node starting from the root and then to the right, at the end we will arrive at some values for each of those. So, if again the left and the right should add up to 1 in all those cases. When you want to find the value or the probability of this word W, what you do is you just multiply it, multiply this one and this one. Okay. So, we are taking these 3 and we obtain the value which will be equal to the probability of the word W 3. So, we need to finally figure out whether the probabilities of all these words really add up to 1. So, if it adds up to 1, then we have really achieved the goal of what softmax has achieved, and it is very easy to prove that it really actually computes the values of all the words, and then if you add each one of them at the end, you will end up with 1. Okay. So, in this case I have just listed in this table the values of W 1, W 2 and W 8 here, and you can actually sum all of these and then find out whether it really gets to the level. Okay. And really it gets to that level. So, that means it is practically now shown that this layer at the bottom contains the normalized probability of all the words in the vocabulary. Okay. So, this is the instead of the one depth softmax layer, now we have an hierarchical softmax layer, and it is defined by the multinomial distribution among all words. Okay. Okay. So, what are the advantages of this? So, why should we really care about the binary tree and the hierarchical model? And here are some of the advantages you will see. One is instead of keeping a flat hierarchy, we now have a binary tree with some depth, right. The depth will be proportional to the size of the vocabulary that you have, and then the path to reach every word is unique. Okay. We have seen that in the previous case, correct. So, every word has a very specific path. Okay. So, as I mentioned earlier, it lays the words in the tree based hierarchy of words as leaves, and you will see that there will be v minus 1 nodes for the left and right traversal. Okay. So, if you have 8 words, you will have about 7 nodes in the tree. Every node denotes the relative probabilities of the child nodes. So, we have if you go back here, every probability defines the relative probability of the child nodes, all right. And then as I mentioned earlier, every leaf represents the probability of the word. So, that is the normalized probability, let us use the right word. So, again explaining further into the advantages of the hierarchical softmax, each node is indexed by a bit vector corresponding to the path from the root to the node. Okay. So, here we append 0 or 1 or 0 according to whether we are taking the left path or the right branch, okay, when we take a decision at the node. Right. The normalized values are calculated without finding the probability for each word. So, instead of calculating the probability of each word using the softmax, the normalized values are calculated without having to really compute that equation 1 that I had shown earlier. It is done based on the product of all the probabilities that starts from the root node to the leaf, okay. And the entire vocabulary is partitioned into classes also. Okay. So, if you look at this, so we can call this as the major class, right. So, this is a binary class and then when you go to the last node you will see the words in classes. So, this is what we are talking about when we mention is a relationship or frequency. We can keep all the words that are related by is a relationship as one group. Okay. For example, if you look at the colors, right, there could be some RGB values related to the colors there. The closer ones which we can mention, for example, we are representing the colors in about 16 different ways, right. So, the color 1 differs from the color 2 by a small fraction. Color 3 and 4 they are close enough, but not very close to 1 and 2 or 5 and 6. So, in that way we can classify them and then arrange the tree in the classified fashion. Okay. And then what the network is going to do is going to learn the probabilistic decisions instead of directly predicting the probability. So, since we are going to be traversing from the root node to the leaf, so instead of computing the probability using the softmax, now it is going to be learning the decisions to move from one branch to the or one node to the other, whether it has to travel to the left or right, and then what is the actual or the relative probability that we need to look at, and then finally take the probability of the word in question. Okay. So, when we do this operation, so instead of having an O V which is the softmax complexity, we are going to be having a log 2 V, which is lot smaller than what we achieved in the softmax. Okay. From the softmax of O or the order, we are going to be having this order. Okay. The path length is going to be 19.9 for a 1 million word vocabulary. Okay. And if you look at the order, instead of 1 million there, it is going to be 19.9, because we are going to be computing only one word at a time and not the entire vocabulary, the probability of the entire vocabulary. Okay. So, that is where the computation complexity comes down drastically. Okay. The speed up is for a balanced tree. This is the speed up V by log 2 V, and then we can use Huffman encoded tree to help arrange the frequently occurring words in a place which is at a shorter distance. So, when you do that, the computation even reduces further down, right. On an average it will be equal to this, but when you arrange them according to the Huffman encoded tree, it will be lot less than this as well, okay, because frequently occurring words will be kept at a place which is very close to the root, and then rest of the words would be placed according to this value. Okay. By using the Huffman encoding, we still get lot more speed. That is in some cases it is shown that it is about 50x faster